Hi everybody, I hope this video finds you well. In today's video, we're going to be working through a couple examples of applying what we did in the previous video, talking about how to use a substitution to solve Cauchy-Euler differential equations. So we're going to take a look at a couple examples of using the results from the previous video, and then we'll also see how we can use our variation of parameters technique when we're working with Cauchy-Euler differential equations as well. So let's jump right in and take a look at these examples. So we're going to try to find the general solution to x squared y double prime plus 7xy prime plus 9y equals 0. So this is certainly Cauchy-Euler because we have our x squared y double prime, xy prime, and our y term. So it is in the Cauchy-Euler form. So remember, we're going to use the substitution here. Substitution x equals e to the z, or if you prefer, you can think about it as z equals ln x. It's just saying the same thing two different ways. Now, from the previous video, without any sort of work, what we found that xy prime can be thought about as d, where d is now the differential operator, the derivative of y with respect to z, our new variable. And x squared y double prime can be thought about as d minus 1. Now, we know this actually simplifies to d squared minus d, but again, just for pattern purposes, it's probably easier to think about it as d minus 1. If we had an x cubed y triple prime, then we know that that would become d minus 1, d minus 2. Remember, the only thing that's sort of bad about this notation, because it is a little bit of shorthand here, is that these d's here represent the derivative with respect to our new independent variable, z. So let's go ahead and replace that. This is going to become d minus 1 plus 7d plus 9 of y equals 0. So there we go. Again, applying that all together there. This guy became the d minus 1, this guy became 7d, and this guy is just 9 there of y equals 0. So if we simplify a little bit, that looks like we're going to get d squared plus 6d plus 9 of y equals 0. And then if we think about the sort of corresponding polynomial, we'd be thinking about r squared plus 6r plus 9 equals 0. I don't know if we need to even do that. We can probably just see the factorization immediately. Just do a little bit of work here. This is d plus 3 squared of y equals 0. So it looks like we get a root of negative 3 with multiplicity 2. So what do our solutions look like here? Well, we'd have y equals c1 e to the negative 3z. Again, make sure you use that new variable because that's what our substitution did here. And then since it's repeated, we have plus 2c2 z e to the negative 3z. Again, this is a z here because that's our new variable. Okay, now we can undo our substitution. You guys can recognize that these guys are really e to the z to the minus 3, if you like, so that you can actually then think about these as x to the negative 3, and this guy being an ln x. Or you can just directly plug this in and simplify. Either way, you should get c1 x to the minus 3 plus c2 ln x to the minus 3. There we go. There's our solutions, our general solution to this Cauchy-Euler differential equation. Not too bad to do this. Again, once we understand how this substitution works, very easy to reduce this into a constant coefficient differential equation and then solve it our normal way. Notice this also shows that even though we got a repeated root here, a root with multiplicity 2, we were able to approach it the same way. We just wrote it as it would look in terms of z and then undid the substitution as normal. Okay, let's take a look at another example here. So we're going to try to find the general solution to this. Notice that this time it's going to be third order. So we're going to just show that our substitution works even if we go an order higher. All right, so we're going to do our substitution. Substitution. E to the z equals x, or if we prefer, z equals ln x, right? However, again, you like to think about it. Now, what do we know about this? Well, we know x y prime is going to be equal to d. X squared y double prime is going to be d minus 1. And x cubed y triple prime is going to be d minus 1, d minus 2. So let's throw those in there. We're going to get d minus 1, d minus 2. There is no term for this guy, so we don't need to pop that in there. We do have this guy, though, so we'll get plus d and then minus 1, all of y equals 0. Okay, now we can simplify that a little bit. That looks like we're going to get d, and then d squared minus 3d plus 2 plus d minus 1 of y equals 0. And that looks like we're going to get d cubed minus 3d squared, then plus 2d, so plus 3d minus 1 of y equals 0. Okay, now you can think about factoring this. You can use some rational roots theorems if you want, or you can just recognize that this is a form of a cubic, right? This is actually d minus 1 cubed, y equals 0. So if you recognize that, right, that's just your standard expansion of cubes formula, and that does work here. So this is d minus 1 cubed. Okay, so what does that tell us? Well, that gives us a single root, r equals 1, with multiplicity equal to 3. So what do our solutions look like? Well, it'd be c1 e to the z plus c2 z e to the z plus c3 z squared e to the z. And again, make sure that when you do that expansion there, you use your new independent variable, z. So remember, every one of those e to the z's is actually an x, and then you can think about any z's by themselves as an ln x. So this would then give us y equals c1x plus c2 ln x plus c3 ln x squared x. And there we go. We've got our general solution to this Cauchy-Euler differential equation, even though this guy was a higher order 3 there, right? Again, all the trick is based on is understanding this substitution, which we proved in the previous video will work in general for any order. Okay, let's go ahead and take a look at another example. So we've got another one here, back to second order, but let's go ahead and see if we can do this guy. So, same approach here. We're going to do our substitution. All right, substitution is going to be x equals e to the z, or again, if you prefer, z equals ln x. Again, this guy is only second order, so we only have to think about two parts of the substitution. xy prime, we know, is going to be equal to d, and x squared y double prime is going to be d minus 1. So this is going to become d minus 1. This guy is just 1 xy, so it's just going to be 1d, so plus d plus 16 of y equals 0. A little bit of simplification, that's d squared minus d plus d, so that's just going to cancel out, plus 16 of y equals 0. Should be immediately clear, this is going to be one with complex roots. Looks like we're going to get plus or minus 4i, and those complex roots are going to just be multiplicity 1. That means our solutions here are going to be c1. There's no real component here, so there won't be any e component. It's just going to be the cosine and sine. So it looks like we get cosine 4z plus c2 sine 4z. Are we in trouble that we ended up with cosine and sine here? No, we can still undo the substitution as normal. Z equals ln x. So we get some weird looking solutions, but they are the right ones. C1 cosine 4 ln x plus C2 sine 4 ln x. And there we go. There's our general solution to this guy, showing you guys what to do in the situation where you get complex roots. Still solve it the same way, and then just go ahead and undo your substitution, and you should be all good. All right, for our last example here, I'd like to show you guys how to sort of mix this new approach to solving Cauchy-Euler differential equations with something that we saw with variation of parameters. In other words, we're going to look at a non-homogeneous Cauchy-Euler differential equation. So let's take a look at one quick example of that. So there we go. This guy is going to be a Cauchy-Euler, x squared y double prime, xy prime minus that 1/4 y, but it's non-homogeneous with that equals to 3x. However, we know that in general, what is this going to look like? We know our general solution is going to be that y homogeneous plus that y particular. So we know that that's how we should approach it. Try to figure out the homogeneous solution and the particular solution. Okay, so let's start with the homogeneous. So for y sub h, we're going to consider x squared y double prime plus xy prime minus 1/4 y equals 0. Now this is our standard Cauchy-Euler here, so we'll do our substitution. Sum x equals e to the z, aka z equals ln x, which means xy prime is our derivative of y with respect to z, and x squared y double prime is d minus 1. So popping that in there, looks like we're going to get d minus 1, plus d minus 1/4, all of y is supposed to be 0. So that looks like we can simplify it as what, d squared, and then that's going to cancel with d. So d squared minus 1/4 of y equals 0. A little bit funky, but we can go ahead and actually factor that because 1/4 is a perfect square. That's d minus 1/2, d plus 1/2 of y equals 0. So we get two roots, r equals 1/2, r equals negative 1/2, both with multiplicity 1 here. So that tells us that the y homogeneous should be viewed as C1. We get e to the 1/2 z plus C2 e to the negative 1/2 z. Again, got to remember we're using our substitution, so everything's in terms of z here. Then we can undo the substitution. These guys can be thought about as e to the z to the 1/2. So we should get that the homogeneous here is going to be C1x to the 1/2 plus C2x to the negative 1/2. Or if you prefer, we have C1 root x plus C2 divided by root x. Those are our homogeneous solutions. Okay, now we'd like to go ahead and find our particular solution so that we can say that all the solutions in general are the homogeneous plus the particular. So let's talk about how we're going to do that. So to do this, though, you've got to remember that variation of parameters was not set up in this format. Variation of parameters was set up in sort of the standard linear differential equation format. When we did variation of parameters, if you guys go back to 8.7, we never made an assumption that it was constant coefficient. But variation of parameters did assume that it was going to be in standard linear format. What does standard linear format mean? Well, it means that we can't have anything in front of that y double prime. So to work on y particular, to determine y sub p, need equation in standard linear format. Doesn't matter if it's constant coefficient. It's not, but we definitely need it in standard linear format. So we're going to divide through by x squared, and we're going to have y double prime plus 1 over x y prime minus 1/4, 1 over 4x squared y is 3 over x cubed. So definitely important to recognize that that's what we're going to be needing here. Now, again, I really just want to sort of mention again here that this moment where we're dividing through by x squared, this should feel very familiar to you guys when you learned like how to deal with first order linear differential equations and you had to put it in the standard linear format to figure out the integrating factor. Again, whenever you're sort of using these things that apply to just linear differential equations in general, you want them to be in that standard linear format. Okay, so now what do we know? We know that that y particular is going to be of the form u1 y1 plus u2 y2, which means it's going to be of the form u1. y1 we determined would be x to the 1/2, y2 x to the negative 1/2. So it would be u1 x to the 1/2 plus u2 x to the negative 1/2. That means then that from our variation of parameters work, right, we know u1 prime, u2 prime are solve the system, and I'll go straight to the matrix format here. The coefficients would be the y1 and y2, so x1 x to the 1/2, x to the negative 1/2, and then their derivatives 1/2 x to the negative 1/2, negative 1/2 x to the negative 3/2, augmented with 0, and then our particular, and then our non-homogeneous piece, which remember now is 3 over x cubed. So we'd want that as 3 over x cubed there. Okay, so got to make sure we use that correctly. Okay, let's go ahead then and actually solve this thing out. Shouldn't be too bad to do this, right? We can multiply this guy perhaps by 1/2 and multiply this bottom one by x to the 3/2. By doing that, we'll get an x to the 1/2 there, and then we'll be able to cancel out. So let's do 1/2. Oh, you know what? Let's just do the bottom one entirely. Let's just do 2 r 2x to the 3/2 times r2. So that would be x to the 1/2, x to the negative 1/2, 0. Then by doing that, we should get x to the 1/2 there. Here we should get negative 1, and then 3x. We should get 6 over x to the 3/2. There we go. Okay, a little bit messy there, but again, just multiplying this guy by 2x to the 3/2, that's going to give us... Oh, no, I'm sorry. My mistake there. I'm off with my fractions. There we go. We just want to multiply this guy by 2x times row 2. Okay. Maybe it's the green pen that's throwing me off here because I don't normally work in that color. Okay. Now if we do that, 2x, the 2 is going to cancel that. The x times x to the negative 1/2 is going to be x to the 1/2. Here we'll get negative 1. X times this is going to be x to the 1 to the negative 1/2. So let's go back. This guy, negative x to the negative 1/2. And this guy over here should be 3. And then we get x squared. My apologies on that. Okay, that looks a little bit better. All right, so now we can go ahead and use this guy to clear that out. So let's go ahead and do that. We'll take R2 and replace it with R2 minus R1. So we get x to the 1/2, x to the negative 1/2, 0. Looks like we get 0, negative 2x to the negative 1/2 when we do that subtraction, and 6 over x squared. So we can then say that this tells us that negative 2x to the negative 1/2 u2 prime is going to be 6 over x squared, which I suppose we can get that u2 prime. If we divide over the negative 2, looks like we should get negative 3, and then we multiply both sides by x to the 1/2. Looks like we should get x to the negative 3/2 there. So there we go. We got our u2 prime. Let's go ahead and then use this top equation to find the u1. So we get x to the 1/2 u1 prime plus x to the negative 1/2 times this u2 prime, which is going to be negative 3x to the negative 3/2, is supposed to be 0. So that tells us that x to the 1/2 u1 prime minus 3x to the negative 2 is supposed to be 0, which gives us that u1 prime is supposed to be what? 3x to the negative 5/2, it looks like. So there's our u1 prime, there's our u2 prime. Now we're ready to go ahead and integrate those. So we'll do that on our next page here. So u1 prime, I think we just said, is supposed to be 3x to the negative 5/2, and u2 prime is supposed to be negative 3x to the negative 3/2. That seems good. So we have u1 then is going to be the integral, 3x to the negative 5/2 dx. So u1, this is going to become, we add 1 to that exponent, so we get negative 3/2. Then we divide by that negative 3/2, which is the same as multiplying by what, that negative 2/3. So that sounds like negative 2x to the negative 3/2. Yep, that seems good. And then u2 is going to be the integral of negative 3x to the negative 3/2 dx. So u2 is going to be x to the negative 1/2. Looks like 6x to the negative 1/2. All right. So this tells us that y particular is supposed to be negative 2x to the negative 3/2 times y1, which was x to the 1/2, plus the 6x to the negative 1/2 times y2, which was x to the negative 1/2. And it looks like if we put all that together, y particular, what is that going to be? 4x to the minus 1 ultimately. So that tells us that our general solution here is y equals the homogeneous component, c1x to the 1/2, plus c2x to the negative 1/2, plus this particular 4x to the minus 1. And there we go. There's our general solution to this non-homogeneous Cauchy-Euler differential equation. So just to recap, because this is a longer example here, the key thing to remember is that when you're working on something that's Cochi, Euler, and non-homogeneous, you're going to use your substitution as is standard to figure out the homogeneous solutions. That's what we did here. But when you go to use variation of parameters, make sure you remember that to determine that particular solution, you have to put it back into standard linear format. If you go back to 8.7, when we introduced variation of parameters, we assumed that it was in that standard linear format. And of course, it didn't matter what these guys were because they don't play a role. But by dividing by that x squared, we did change what the non-homogeneous component was, which of course determines part of the system, which of course influences the solutions that we get there. So there you guys go. This actually concludes our discussion of higher order linear differential equations. You now know how to deal with homogeneous and non-homogeneous constant coefficient and homogeneous and non-homogeneous non-constant coefficient as long as they're these Cochi Eulers. And to be honest, outside of some very specific situations or numerical approximations, these are about as far as we can go in terms of having nice general ways of solving higher order differential equations. In our next video, we'll be moving on into chapter 9, which is our last chapter, talking about how to work on systems of differential equations as opposed to higher order differential equations.